Hi, I'm Shahar. I'm an engineer in Starkware, and I'm one of the co-creators of Cairo, which is what I'm going to talk about today. Clicker. Don't have it. Okay. Okay. So what is Cairo? First of all, it's based on a white paper we're releasing soon. If you want to check it out, it's a joint work with Lior Goldberg. It's joint work with Lior Goldberg and Michael Ryabzev and myself. Well, first of all, it's... Oh, okay. Sorry. Oh. No. Nope. The back does not work. Okay. Okay, so this is a proof system for computation integrity, which basically means we have two parties, a prover and a verifier. The prover is trying to prove some computation he did and trying to prove that the computation was correct and we got some output. And the verifier looks at this proof and can say whether it's true with high probability or it's not true. And this is based on the Stark proof system, if you know it. The main benefit you get from Cairo is that it is easy to use. It has a programming interface, unlike Stark. I'll immediately show you what you need to use Stark, but it's not that trivial. And Cairo is supposed to make it very easy to use. And also, one of the greatest features of Cairo is that it does this as efficiently as possible. Okay, not as efficiently as we managed to make it. Yeah. Okay, this is not the first solution for a proof system which has a programming language interface. There are some existing ones. The difference is that most of them are like libraries for creating circuits, which means there are a lot of downsides in that approach. First of all, it's not Turing-Complete. What these solutions usually do is take the code a user writes and compile it to a list of polynomial equations and variables. And that means that every time you have, for example, a branch or a loop, you need to assign specific variables to every possible flow, which restricts what you can do very greatly. So Cairo is the first production-grade proof system, which is also Turing-complete in this context. It implements a von Neumann architecture. We use it today or over Ethereum. There was already like $2 billion, a lot of money, things. And we also have extensive tooling. If you're interested, you can check out our site, cairolang.org. Okay, so a few preliminaries. What is Stark, which is a proof system we use? Like I said, it's a proof system. It's pretty efficient in the sense that the proof time is quasi-linear, and the verifier time is polylogarithmic. It's also transparent, which means you don't have to do a setup, which is a complex thing at the beginning that is not that, in some contexts, not that secure. Well, Stark is transparent, which is awesome. And it uses an array representation, which is the main problem, I would say, with easily translating statements to Stark. Well, just a bird's eye view. I have some statement I want to prove. For example, let's say I have 1,000 transactions between users. I want to prove that each one is signed correctly, and when I apply them, no balance goes under 0, and the result state is something. This is like a statement I can describe in words. I can pretty easily describe it in code. I need then to translate it to an error, which is a bunch of polynomials and variables, which is not always very trivial. If I manage to do that, then I can mostly throw it on a bunch of algorithms and call it Stark. So how does an error look like, this representation? We have this table we call the trace. It has some constant number of columns, and number of rows is a variable power of 2. Each element is a field element, which we work in. We work in like a 256-bit field, more or less. On this table, we have some constraints which describe this computation. These constraints are polynomials of supposed to be low degree, and they're repeating every power of 2, some power of 2. It depends on your constraint. For example, if I wanted to prove the computation of the Fibonacci sequence, I could have had 2 columns like here, and I could have one constraint that says that xi plus 1 is yi, which is just copy the last y, and that the next cell is the sum of like yi is xi plus yi minus 1. So just some constraint that describe the evolution of the state from one row to another. In Fibonacci, it's pretty easy. In real-world uses, it's not that trivial, especially if your logic is not repetitive. For example, in some computer programs, you want to do a bunch of things of one type and then do other stuff. So translating to error, which is repetitive and local, is very hard. Yeah. Just a few notes about efficiency, because we'll use it later. We measure the efficiency of the error mostly by its size. If you have more rows, more columns, more cells overall, then the prover will have to work harder. Other than that, we want low degree of the constraints, and the number of constraints and how hard it is to compute these constraints. This affects mostly the verifier, but also a bit the prover. So we want to minimize all of this when we build an error. Yeah. Okay, so what is the motivation of creating Cairo? Like I said, designing errors is hard, and the solution we wanted to take is create a single error. We do it only once, and it will prove the computation of some universal machine. And on top of this universal machine, we can run code. We'll have some programming interface, and hopefully we want to make this as efficient as possible. Okay, so this universal machine, we chose to make it in a von Neumann architecture, which is the common architecture today in CPUs, for example. It basically means that you have some memory, and your code lies in this memory, and your CPU has cycles, and at every cycle you fetch some instruction from that memory, you decode it, understand what you need to do, and then you execute it, and then go on to the next instruction. Second thing we have about this VM is that it uses the non-deterministic continuous read-only memory, which is like very long, but it's not the standard memory you'll get in CPUs, because we have different considerations when we use error. Things that are efficient in CPUs are not very efficient in errors. I'll touch it a bit later, but it's basically, it acts like a write once memory. It needs to be continuous in the address space. So for example, all the addresses I use are like between 0 and n for some n, and I use all of them. And also another benefit in this virtual machine is that it's non-deterministic, mostly because of the nature of Starks. Starks, I can have some cells that are unconstrained, and then I can have their values come from I don't know, an oracle or something, perhaps the prover will need to fill them correctly, but it's not affecting the tray size, so it's good. So a few design choices and why we made them. Unlike modern CPUs, which has tens of registers in them, we only have 3 registers. Why? When we need to choose a register in the execution phase, in CPUs we have big multiplexers. If we had a multiplexing equation, which is very big, uses a lot of variables, we have a very big constraint. It says like A times first register plus B times second register plus blah, blah, plus, and it comes out like a very big constraint, and we don't want that. That affects the verifier. However, the memory is a lot cheaper in errors compared to modern CPUs. In modern CPUs, accessing the memory can take a very long time. However, with our model, we can use it only 5 tray cells for each memory unit, which is pretty efficient in this context. And another thing which we chose is the decoding of instructions. In modern CPUs, when you have some instruction, you need to put it in some table, look up in the table, and get the control flags to decide if you want to add or multiply or fetch from a memory, all the different possibilities you have. You have some flags, and you look up in the table to get it. So looking up in the table is hard in R, so we don't do that. Instead, we just trivially encoding this instruction. We just take all the control flags and concatenate them, and this is the encoding of the instructions. This means that we have a lot of invalid opcodes, but it doesn't really matter for us. And like I said, the memory model, and the basic data type is a field element, because this is how the array works. So a few things about I can't show the entire array because it's very meticulous and will take a long time. So a few I'd say highlights about how the array and the equations do look like. First of all, the memory, which is the nicest part. And like I said, we only need 5 cells to have a memory unit. So how does a memory unit look like? We can have a column of address and value. And what we want to prove on these columns is that every time we have 2 rows with the same address, then both of the values are the same, which is basically a read-only memory. We want to prove that this is basically a function from address to value. Okay, so first of all, it's not that trivial in the first look, because all the constraints we have in R are local constraints. Something like this row and the next 2 rows have some polynomial working on them. And this, what we need here is some global constraints that works across all the rows. So what we use is a permutation trick, which is due to Bayer and Groth. Basically, we can prove that we can introduce 2 new columns, address prime and value prime, and then prove that the multi-set of pairs address value are the same in both. Basically, what we do is randomize 2 values z and w and prove that the product of all these things, as you can see, z minus a minus wv, the product is the same in both, which basically means if you take this polynomial x minus a times x minus b times x minus c, which represent the multiset of a, b, and c, then the polynomial is the same on the previous columns and the new columns. Okay, so now we have these new columns, and basically want them sorted by the address. So the prover will sort them, but we still need to verify that they are indeed sorted. So because of we assumed continuity of the address space, then all we need to do is verify that the difference between this address and the next address is either 0 or 1. This is a local constraint, which is awesome. And it's very simple. It's either 0 or 1. It's a degree 2 polynomial. And once we did that, we also have degree 2 polynomial to show that either the address is different, which is okay, but if it's not different, then the value needs to be the same. So it's also degree 2. And overall, we have 5 cells, 2 for the original address value, 2 for the new address value, and 1 for the permutation trick we had before. So it's 5, and it's pretty cheap. Again, this assumes the read-only continuous memory. And that's why we chose this model. It's good enough for actually programming in it, especially if you go for a functional like language, and it comes out very efficient. We also need some range checks, verifying that some element is like a number between 0 and 2 to the 16 minus 1. It's not very trivial to do this efficiently. Usually you'll need for like 16 cells to do this. Each one checks a bit, and then you have 16 bits, and you add them. But we want to do it with less. This is 3. What you do is just assume we have a lot of rows, and all the value, the entire column we want to show it's in range, actually fills up the entire range, 0 to 2 to 16. And then we do the same trick from before. We sort the values. After it's sorted, we verify that the difference between each two is either 0 or 1. So instead of 16 cells, we have just 3 cells. Decoding, like I said before, instead of looking up at tables to get the control flags, we just do a simple split to bits, most of the flags, except of the other than the flags, we also have 3 numbers in the range of 16 bits we need. So basically, we have 3 range checks for, like we saw on the last slide. We have 16 bits, and then we have this constraint that the value we just read from the code segment is the sum of these 3 constants and the flags. Just no tables, and it's pretty okay. And the next execution is it's pretty straightforward, I would say. We have all the control flags we need, so we want to keep it degree 2 because it's nice. And the way we implement the multiplexer, okay, because there are multiplexers, for example, in the operation we do, if we add or multiply or just take the right one or do a reference, all these are in a multiplexer. So if we want to choose between n different expressions, instead of using log n bits, we use n minus 1. If we use log n, we would have a higher degree for our multiplexer. To keep it degree 2, we have n minus 1 flags that just either exactly one of them is 1 and the other are zeros, or everyone is 0 and this is the other one. So this is like introduces a couple of invalid opcodes where we have more than 1 bit which is on, but we just treat these as invalid programs. And the last thing which makes a lot of the benefit to the efficiency is, I'd say, the built-ins. Now, we can extend this error with a bunch of other errors we have, like hashes and verifications and other stuff, and they just communicate through the memory. Both have access to the same memory, and just communicate through it. So, okay, about 50 trace cells, and it's pretty efficient, and that's it. If you want to, we have this site here, QR codes. You can join the Cairo Dev Discord, And we are hiring. If anything here is interesting, it's interesting to me. So I'd love to see you here. Thank you.
Questions, please. How feasible is it to write something like an LLVM backend to target this?
Well, we looked at it a bit at creating an LLVM backend. LLVM assumes what?
Can you repeat the question, please?
Yeah, I will repeat the question. He asked how feasible it is to have an LLVM backend for this. Well, LLVM backend just has a few assumptions which, on first glance, we didn't see how to overcome, but the machine he uses and the memory model he uses. So, if you want to help us use it, we'll be very glad, but we didn't see a very easy way to use LLVM.
One more. Yeah.
How would it compare proving something in the universal machine like in Cairo to just proving specifically the program you want, like in efficiency?
In real world terms, we had this program before which we used for a decentralized exchange, and when we converted it to Cairo, it was not a lot less efficient, just about 1.5, 1.2, but using Cairo let us do a lot more complex logic and use optimizations that you wrote in code, which actually made it a lot more efficient. So, it depends if you can do some complex logic, if it allows you doing optimizations, but it's pretty much comparable, especially if you use built-ins. Okay, thank you very much.